Duffin, back with CFT and Lorentzian signature.
Okay, thanks a lot. So last time we discussed in detail a model of a quantum field theory as a quantum mechanical system whose Hamiltonian is bounded from below but unbounded above. And we found that, so first of all, there's this relationship between Lorentzian operators and Euclidean operators. And one can define Whiteman functions, namely Lorentzian correlators with a particular ordering, as boundary values of analytically continued Euclidean correlators. And the specific prescription was that one should analytically continue the Euclidean times so that their real parts are ordered in the way that we want the Whiteman function to be ordered. And when we do that, then we stay inside the regime of holomorphicity of the Euclidean correlator. We can then continue the imaginary parts of the Euclidean times, which will become the real parts of the Lorentzian times, to anything we want. And then finally take the limit as the epsilons go to 0, where when we take the limit, when we approach the boundary of the regime of holomorphicity, we naturally get a tempered distribution and not just a function. Okay? So this was the prescription that we arrived at last time. And what we're going to do now is start by just generalizing this prescription to quantum field theory. So we're just going to introduce the spatial directions. And essentially, we've done almost all the hard work already. Essentially, the spatial directions come along for the ride, and the prescription for understanding Whiteman functions in quantum field theory is just going to be exactly this prescription, but dressed up a little bit. So we're going to talk about quantum field theory. And I'm going to work in mostly plus signature. So the metric is minus dx0 squared plus the spatial component squared. And this is because this is the only correct Lorentzian signature. The other one is incorrect. So as before, we can start by writing down Heisenberg picture operators. And these are given by conjugating O of 0 by the operator that moves you in space-time. And it looks like this. O of 0 and e to the I p dot x. And if you're confused about signs, so by the way, p, these are the energy momentum generators. And if you're confused about signs, the signs are fixed by requiring that the t dependence of this term be e to the minus I t times h, where h equals p0. And remember that minus I was dictated to us by Schrodinger 100 years ago. So that's why we have a plus sign here and a minus sign there. Okay, so these are the Heisenberg picture operators, and we can now consider a correlation function of them. So let's look at a Whiteman function in QFT. So we just take a product of these operators. As before, we'd like to think about this not just as a function, but as the boundary value of a holomorphic function. Where is the regime of holomorphicity? So let's consider giving the points both real and imaginary parts. So we'll write xk is yk plus I zeta k, where y and zeta are both real. So these are vectors in Minkowski space. When we do this, the operators in the Whiteman function are then separated by these factors. So for example, let's look at O1, O2, plug in this definition of the Heisenberg picture operator, and we find that O1 and O2 are separated by the operator e to the I p dot x12, which is e to the I p dot y12 minus p dot zeta 12. Now, the analog of the statement from before that the Hamiltonian has a positive spectrum in QFT is the statement that the spectrum of p is contained inside the forward light cone. So is in the interior of the forward light cone. And I'll write that in this notation. So being greater than or equal to 0 means something is future directed or null in this notation. And what this means is that if we choose, let's see, yeah, so that means that if we choose zeta 1, 2 to be past directed and time-like, and another way of writing this is zeta 1 is less than zeta 2. So if zeta 1, 2 is past directed and time-like, then it implies that this quantity minus p dot zeta 1, 2 is negative. And that gives us exponential damping of high energy states. Okay, and that exponential damping of high energy states makes the correlator beautifully convergent and holomorphic in this region. So it means that the regime of holomorphicity in a QFT is zeta 1 less than zeta 2, and a similar argument tells us that we need each vector here to be in the past of the previous one, of the next one. Okay? So this is the condition. If the imaginary parts of the positions satisfy this condition, then the correlator is holomorphic. Okay, any questions? Okay. So this gives us a recipe for computing Whiteman functions in QFT. And it's essentially the same recipe as before. The idea is to approach the Whiteman function from inside the region of holomorphicity. So specifically, in practice, we can say start with the points real and space-like. And then give their times imaginary parts so that we move them so that they're definitely inside the regime of holomorphicity. So we give the x sub I imaginary parts zeta I, which is the imaginary part of x sub I, satisfying this condition for holomorphicity over here. And so, for example, we could set their times. If we start with them all space-like, we could then set the times equal to minus I epsilon I, where the epsilons are ordered in this way. Okay, and so that is essentially just doing what we already did in quantum mechanics. So remember, if the Lorentzian value of the time is minus epsilon I, that corresponds via the dictionary up there to the Euclidean time being epsilon I. Okay, so this prescription here is the same as that prescription up there. Okay, and so now we continue the real parts to whatever we want. And then finally take the imaginary parts to 0, staying, well, take the imaginary parts to 0 from the region of holomorphicity. Okay? So that's the prescription, and it's really just the same prescription that we had in quantum mechanics, souped up a little bit. Okay? Any questions? Okay, so let's do an example. We'll look at a two-point function of a scalar operator in a CFT and use this algorithm and figure out what the Whiteman two-point function looks like. So in Euclidean space, let me split the, I'll choose a time direction, and I'll call that tau, and I'll call the spatial directions x vector. So the two-point function in Euclidean space is constrained by conformal invariance to be equal to just the distance to twice the scaling dimension. Which I can write like that. And so delta here is the dimension of O. And so let's now try to compute the Whiteman function, where I'll just choose an ordering. So we're going to compute the ordering where the point 2 is later in the Whiteman function than point 1. And by the way, when I write from now on, when I write operators without an L or an E subscript, I'm going to mean Lorentzian operators. Okay, so according to this prescription, what we should do is start by setting the Euclidean times equal to some values such that we can approach this correlator from within the regime of holomorphicity. So that means that we should set tau 2 equal to epsilon 2 and tau 1 equal to epsilon 1 with epsilon 2 bigger than epsilon 1. Okay? So the operator that's later in the correlator has to be at later Euclidean time. And then the next thing we do is continue these epsilon i's by adding imaginary parts, which will become the times of the operators in Lorentzian signature. Okay, so what we end up with is this Euclidean correlator evaluated at epsilon 2 plus I t2, x2, a Euclidean of epsilon 1 plus I t1, x1, and that's just given by plugging these time coordinates into this expression. And if we like, we can expand this out. 1 over epsilon 2 1 squared plus 2I epsilon 2 1 t2 1 minus t2 1 squared plus x2 1 squared to the delta. Okay. And finally, the last step is to just take epsilon 2, 1 to 0. And I'll call that epsilon. So we're going to take that to 0. And the final result is that O of T2, x2, O of T1, x1 is the limit as epsilon goes to 0 of 1 over. We can combine these two things into just the norm in Lorentzian signature. And since we're taking epsilon to 0, we can ignore this term compared to the other terms. So this just becomes x21 squared plus I epsilon t21 to the delta. Okay, now we have a complex number raised to a non-integer power in the denominator. But the whole point of this exercise is that the phase of this quantity is unambiguous. It's fixed by our prescription for computing this. The prescription says that when t21 is equal to 0, the 2-point function should be positive because it's equal to Euclidean 2-point function. And then the value of the phase of this thing should be obtained by continuing in t21 from that region at finite epsilon. Okay? And so I'll leave it as an exercise. Compute, and the answer is in the notes. Compute the phase of the 2-point function in the different regions. So when x21 is space-like and future pointing, when is time-like and future pointing, when x2 is space-like from x1, so this is time-like future pointing. This notation means space-like, and then finally the other direction. Okay. Good. So if we wanted to compute the other ordering, we can just see the answer by swapping 1 and 2. And it's the limit as epsilon goes to 0, 1 over x12 squared plus I epsilon t12 to the delta. And the two answers only differ in their I epsilon prescription. And the I epsilon prescription only becomes important when you want to continue out of the space-like region. So if we start with the two operators space-like, then this thing is real and positive, and the I epsilon term doesn't matter at all. It only starts to matter when the two operators become light-like, and one of them starts, and as you're moving one into the interior of the future null cone of the other operator, when that happens, you encounter a branch cut, and the I epsilon prescription tells you how to move around the branch cut. Okay? So in particular, one consequence of these two formulas is that these two different orderings in the Whiteman function agree with each other when the operators are space-like. And in particular, that means that the commutator of the two operators, at least the expectation value of the commutator, which is what we've computed, vanishes when the points are space-like separated, which is consistent with what you'd expect in a causal theory. Okay? Any questions? Okay, good. I guess one more comment that I should make about this is that the objects that you get, the Whiteman functions that you get when you do this procedure, being boundary values of holomorphic functions, they become tempered distributions on Minkowski space. In particular, they have singularities. They appear to have singularities. So, for example, when the two operators become light-like from each other, there's a singularity in the Whiteman distribution. But these singularities are integrable against Schwartz functions. Okay, and part of the content of the Osterwalder-Schrader reconstruction theorem is that if you start with a reflection positive quantum field theory in Euclidean space, then after analytic continuation, you get tempered distributions on Minkowski space. So in particular, you shouldn't be scared of the singularities in Whiteman functions in QFTs, just in the same way that you shouldn't be scared of the Whiteman distributions in quantum mechanics that we talked about last time. Okay. All right. So we're now going to use this fact to do acute computation that will require integrating these singularities, and the singularities in the Whiteman distribution will be totally fine. They'll let us integrate them, and we'll get a cool result. Okay, and so what this is, what I'm going to talk about now, is a Lorentzian proof of the unitarity bounds. So you saw proof of the unitarity bounds in Slava's lectures, is that right? Did he talk about the and Leonardo also talked about them? Okay. So there's a right. So the unitarity bounds for a traceless symmetric tensor operator in a CFT say that the dimension is bigger than d minus 2 over 2 if j is equal to 0. So here j is the spin. And j plus d minus 2 if j is bigger than 0. Okay, those are the unitarity bounds. And the argument that you presumably saw for the unitarity bounds comes from studying descendant states in radio quantization. So you start with a primary state, not omega, definitely not omega. You start with a primary state in radio quantization, and you can study its descendants by acting with momentum operators and demand that the norms of these descendant states are positive in radio quantization.
Sorry, what's the definition of J?
J is the spin of the operator.
Well, general dimension.
Good. So this is just the unitarity bound for traceless symmetric tensors. I'm only going to talk about that case for simplicity. That's right. So for non-traceless symmetric tensors, there are more complicated unitarity bounds that one can try to work out. Okay. So good. So the idea was to study some descendant state like this in radio quantization and demand that the norm of the state is positive, and demanding that the norms of states are positive give constraints on delta and j. And in particular, the j equals 0 case, this bound that delta is bigger than d minus 2 over 2 comes from studying descendants at level 2, by which I mean two momentum generators acting on the primary. And the bound for j bigger than 0 comes from studying descendants at level 1. Did you see these calculations in the lectures? Sort of? Getting mixed signals. Okay, sort of. All right. Well, good. Okay, so this is relatively standard. It's the way that people usually present unitarity bounds. Now, there's an issue with this argument, this way of arguing, that positivity of some descendant state only gives a necessary condition for unitarity. To get sufficient conditions for unitarity, you need to check positivity of all descendant states. So it's not enough to just check level 2. You have to check that level 3, 4, 5, and so on don't give additional constraints. In fact, I'm not sure I've seen like a clear presentation of that in the literature. I think it's glossed over in most discussions. So there's a different way of proceeding that is an intrinsically Lorentzian way of proving the unitarity bounds that immediately gives both necessary and sufficient conditions for unitarity. Okay, so the Lorentzian proof of the unitarity bound is due to Mach. And I think it may actually be the first way that the unitary bounds were derived, but I'm not certain about that. Okay? And I like it because, again, it gives a familiar result, but it also, to really make conceptual sense of it, you need to understand the machinery that we've developed so far. Okay, so the idea is that, so we're going to work in Lorentzian signature. The states in a conformal multiplet, so let's consider O to be a scalar for simplicity. The conformal multiplet of O is spanned by states obtained by smearing against test functions. Okay, so this is a set of states that spans the conformal multiplet of O, and unitarity is equivalent to the condition that the norms of all such states should be positive. So what is this norm? It's plugging in this expression. It's an integral dx1, dx2, f star of x2, f of x1. So remember here, f is some Schwartz function. In particular, it takes complex values. So it's a Schwartz function on Minkowski space. And so f star is its complex conjugate. And this multiplies the Whiteman two-point function. And the Whiteman two-point function is something that we just worked out over there. And I'll call it k of x2 minus x1, k for kernel. So the statement is that this integral should be positive for all test functions all test functions f. And another way to say that is that this kernel should be a positive definite integral kernel. Okay? Now, if you have a kernel and you want to prove that it's positive definite, the first thing you should do is try to diagonalize it to the extent possible. And this kernel is translationally invariant because the two-point function is translationally invariant. And a translationally invariant kernel is diagonalized in momentum space. Okay, so let's go to momentum space. And it's crucially important here that the Whiteman distribution, as a tempered distribution, has a Fourier transform. And so we can do this. We can go to momentum space and not have to worry about having to regulate singularities or anything like that. So this expression in momentum space is just equal to the integral d dp 2 pi to the d of k tilde of p times the absolute value of f tilde of p. So here f tilde of p is the Fourier transform of f of x. K tilde of p is the Fourier transform of k, which I'll write in a second. And OK, so we've diagonalized the kernel. And you see now that unitarity is equivalent to the statement that k tilde of p is a positive function, but not really function, right? It's not a function. It's a positive tempered distribution. On momentum space. Okay, so all we need to do is compute the Fourier transform of the Whiteman two-point function and check whether it's positive. Okay, so let's do that. So k tilde of p is equal to the integral of the Whiteman function e to the minus I px. And of course, this is the thing that we computed earlier, 1 over x squared plus I epsilon x0 to the delta. Okay, so so how do we actually compute this? Well, so the first observation is that this Fourier transform is proportional to a theta function that enforces that p be inside the forward light cone. You can convince yourself of that through the same way. It's the exact same theta function that we talked about last time. So last time we were doing a Fourier transform of a one-dimensional two-point function. And the reason that the Fourier transform had a theta of omega in it was that you just look at, you plug in the definition of this Heisenberg picture operator, and you see that when you take the Fourier transform, you're picking out the spectrum of that operator, and the spectrum is positive. Okay, so there's a theta of p here. And the meaning of theta of p is that p is bigger than 0. And this notation again means that p is inside the forward light cone. And so that means that to compute this Fourier transform, one thing you can do is you can choose p to be time-like and future-directed, and use symmetries to fix p. Okay, so we can choose, because this is Lorentz invariant, we can choose without loss of generality that p is equal to p0, comma 0, 0, 0, 0. And now the integral has SOD minus 1 invariance in the spatial directions. Okay, and so I'll just write part of the expression. So the idea then is that so we're going to fix p is p0 dot dot dot, and when we do that, we get an integral with so we just get the integral of our Whiteman function minus t squared plus x squared plus I epsilon t to the delta times e to the I p0 t. Okay, and now you can see you can do the integral over the spatial directions first. When you do the integral over the spatial directions, you actually land on the Fourier transform of one-dimensional two-point function. Okay, so after doing the integral over the spatial directions, it just modifies the power appearing here and gives you some extra gamma functions, and you land on exactly the computation that we had to do last time. Okay, so you can look in the notes to remind yourself how that computation worked last time. I'll just write down the answer. The answer is you get some gamma functions. So there's a 2 to the d minus 2 delta times 2 pi to the d plus 2 over 2 over gamma of delta minus d minus 2 over 2 gamma of delta p0 to the 2 delta minus d. And then, of course, our theta function of p0. And this part we can immediately covariantize. So this is the same thing as minus p squared delta minus d over 2 times theta of p. Okay? So that's the answer. I encourage you as an exercise to do the computation for yourself and convince yourself that this is the correct answer. And so now the key point is that factor right there. So the gamma function is positive when its argument is positive. It has a pole at 0. And when you go to the left of that pole, when you go to negative values, it becomes negative. Okay, at least initially. And so you see here that this thing is positive if delta is bigger than d minus 2 over 2. And that is indeed the correct unitarity bound for a scalar operator. Okay. Yes? So I did this integral in a way that such that I didn't have to think about that very carefully. The phases. Okay, sorry. The question was, how did the phases of the integral come in? In the way that I did the integral, you do the integral over the spatial part first, and then you're left with a one-dimensional integral. And the one-dimensional integral, let me remind you of the integral we had last time. So it was an integral dt e to the I omega t over epsilon plus I times t to the 2 delta. Okay, that was the integral we did last time. That's the one-dimensional version of this problem. And this integral has a similar property. It has different phases in different regions. Okay. Now you can do the integral by breaking up into the different regions and computing the integral in the different regions. But another way to do it is just use some conservative manipulations to remove the phases, which is what we did last time. So you can do it any way you like. Another way to do this computation would have been to break up the x integral into different regions: future light cone, past light cone, spatial regions. But I think it's a little nicer to do it all at once. And the fact that you have a Whiteman distribution, the fact that the singularities of this function have this very special structure, that they're integrable. That tells you that the different regions are connected to each other in a very important way. And it means that you probably shouldn't try to break up the different regions if you can avoid it. Okay, yes?
What happens if the delta lands on the pole?
Good. So you mean if delta equals d minus 2 over 2.
Yeah.
Good. That's what I was going to explain next. So there's some interesting subtleties with this proof of the unitarity bounds. So what if delta equals d minus 2 over 2? So the gamma function has a pole. It's in the denominator, so we get 0. But not quite. We get 0, but the 0 multiplies minus p squared to the minus 1. Okay? So if delta equals d minus 2 over 2, then we get 0 times minus p squared to the minus 1. Okay? What's going on is that this expression that I wrote for the answer is not a good expression anymore. The answer, whatever it is a tempered distribution of some kind. When delta equals d minus 2 over 2, this is not a good way of writing that tempered distribution. The correct answer is, you might be able to guess it, it's delta of p squared. Okay? So it's a delta function localized on the null cone. And as a sanity check, you can check that this, for example, has the right scaling dimension. It's the same scaling dimension as this. So this is, morally speaking, a delta function. And if you do the do the integral carefully, starting from this case, you'll indeed find the delta function. Now, an important point about this delta function localized on the null cone is, first of all, this is what you get in a free theory, right? In a free theory, in a free conformally invariant theory, particles propagate with null momenta. Okay, and so this is the correct answer in a free theory. Second of all, it's positive, right? This is a positive distribution, and so this case is still allowed. Okay, it's still unitary, and so we can say that this is a positive tempered distribution if delta is bigger than or equal to d minus 2 over 2, which is really the correct unitarity bound. Okay, so there's some more subtleties. So now, what happens to this gamma function if we go beyond d minus 2 over 2? So we go to the left of d minus 2 over 2, the gamma function becomes negative. And clearly, this isn't a positive distribution anymore. But the gamma function has repeated poles, and it switches sign every time you pass a pole. So let's go even farther down in the argument of the gamma function to where it becomes positive again. Is this unitary? The answer is no. And the reason it's not unitary is because it becomes positive times minus p squared to some negative power. And we need to be careful. and define what this really is as a tempered distribution. Okay? If I just write minus p squared to a negative power, it doesn't tell you how to integrate it against the test function. You have to explain how to integrate it against the test function. And if you study carefully the light cone of this tempered distribution, you'll find that there exists basically the singularity there has some structure. So you remember last time I talked about how you should think of the singularities of Whiteman functions as kind of having some oscillations in the middle that make the thing integrable, even if it doesn't seem like it will be integrable. That's indeed what happens here. And if you multiply by the right test function, you can pick out the negative parts of these oscillations. Okay, so that's a very woo-woo explanation. The correct statement is that when delta is below this value, there exist test functions that can be integrated against this that give negative values. Okay, so it's really only positive as a tempered distribution in this range. So it's a lot more subtle than the usual proof of the unitarity bounds because, well, you have to do this kind of hard integral. And then after you do the integral, you have to think a lot about the answer. But on the other hand, it gives you the complete unitarity bound, necessary and sufficient conditions. It shows that if you were to study higher levels over here and compute whatever norms you want, you're never going to get new conditions. Yes?
How do I see that this is sufficient?
That this is sufficient. So the idea is that, this implication goes both directions. So the implication there, unitarity is equivalent to the statement that all the norms of the states are positive. That's equivalent to the statement that k tilde of p is a positive tempered distribution. Okay? Because the norms of the states have this form. Okay. Yeah? Oh, okay, good. Yeah, the question was, why can't you play the same game in Euclidean signature? Maybe you can. Yeah, I'm not precisely sure, but yes, I mean, you should be able to. I mean, unitarity should be equivalent to positivity of all smearings in Euclidean signature of the two-point function, and maybe you can do the analysis in that case. Yes.
I think the answer is no, but is there any version of this argument that would allow you to derive the Katz determinant for C less than 1 models?
Okay, good. The question was, is there a version of this argument that might let you derive the Katz determinant, for example, in 2 dimensions? And there's an analog of the Katz determinant in higher dimensions, which is the determinant of norms, the determinant of inner products of all descendant states with respect to the global conformal group. And I don't know the answer. Yeah. Yes?
If you do this in Euclidean signature, I guess I can get a principal series.
Well, there's a correct. So the question was, do you get the principal series in Euclidean signature? So the principal series representations are unitary with respect to a different kind of norm. So if you wanted to do this argument in Euclidean signature, you'd have to start with the correct norm that should actually be positive, which is the norm where you have the test function and you reflect it. So it's the norm that you get in a reflection positive theory. Then you're not going to get principal series representations. Yes?
Is the subtlety coming from the order of integration for x and t?
No. You should be able to do the integral in any order you want.
It seems that when t is 0 or not, the integral of x will be different answer.
Do you mean the subtleties here?
No, like upwards.
When t is 0 or not, the integral over x will give different answers?
Right.
I mean, this distribution is defined by analytic continuation. As a function of t, t moves in a holomorphic region. Okay, so no matter what x is, so you should be able to do the integral over x for any t. In fact, you can do the integral over x for positive t, and then if you want to know what the answer is for t equals 0, you should continue from positive t to t equals 0, because there are just no singularities on the t-axis by construction. Okay. Good. So I won't have time to talk about it, but you can, of course, generalize this. So we just did this for scalars. You can generalize it to spinning operators. The only hard part is computing the Fourier transform of a spinning two-point function. And if you're curious, you can look in the notes for an example of doing this in the case of spin 1. Okay? Okay. Good. So there's a surprising fact about conformal field theories in Lorentzian signature that I want to talk about next, which is that, well, and it won't be surprising to those of you who've studied ADS-CFT. The statement is that there is life beyond Minkowski space. So in a conformal field theory in Lorentzian signature, you can actually continue the correlators beyond Minkowski space and talk about physics beyond Minkowski space, and I'll explain what that means. And not only can you do this, but you're guaranteed to be able to do this in any conformal theory. So there's a whole bunch of extra structure and extra observables that you get for free in a CFT. And I want to talk now about how that happens. Okay, so the idea, again, for going from Euclidean to Lorentzian signature is that let's say you start in Euclidean, you choose a time direction tau, and then you write tau is equal to epsilon plus it, staying inside the regime of holomorphicity. Now, the choice of time direction tau is equivalent to a choice of Hamiltonian. And in a conformal field theory, there are other choices of Hamiltonian that you might make. And the claim is that by choosing a different Hamiltonian from the naive one, you can analytically continue farther than you previously thought. Okay? So I want to explain how that works. This is a result due to Lucier and Mack, an old result. And the best way to understand these kinds of statements, so first of all, the Hamiltonian that they used is a kind of funny Hamiltonian, 1/2 P0 minus K0. And the idea is to write the correlation functions in terms of a time coordinate that's conjugate to this Hamiltonian, and then analytically continue in that time coordinate. This might sound like a kind of confusing thing. So the first thing I want to do is introduce some formalism that allows you to think about the action of different conformal generators in a very clear way, and that's the embedding formalism. Okay? So we're going to develop a little bit of technology. Once the technology is developed, we'll be able to understand this result of Lucier and Mack. Okay, so let's talk about the embedding formalism. And by the way, have you seen the embedding formalism in any of the lectures so far?
Yeah,
Slava talked about it. Oh, great. Did he introduce it and everything? Oh, he did? Oh, okay. Great. Okay, so I'm going to speed up. Okay, so let's start in Euclidean space. So the Euclidean embedding space is Rd plus 1, 1. And it's acted on by the Euclidean conformal group, SOD plus 1, 1. And on this space, I'm going to choose coordinates x plus, x minus, x mu, with metric minus x plus, x minus, plus sum from mu equals 0 to d minus 1, x mu squared. And the idea of the embedding formalism is to realize space-time as a submanifold of this space where the conformal group acts linearly. So in particular, the conformal compactification of Euclidean space, which is the d-sphere. Okay, so by that I just mean Euclidean space plus the point at infinity, is equal to the projective null cone in the embedding space. So these are the points x in the embedding space, such that x is null, modulo rescalings. And our favorite place in the embedding space is the Poincare section. So the idea is that we have the null cone in the embedding space, which looks like this. When we mod out by rescalings, we're projectivizing, and so that means we have we're restricting ourselves to some slice of the null cone. And by choosing different slices, we get different conformal classes of metrics on this space. And our favorite slice is the Poincare section. So the Poincare section is looks kind of like that. It's where you cut the embedding space with a plane. With the plane x plus equals 1. And so a null vector on the Poincare section has the form so here we can plug in x plus equals 1 and then solve the condition that this thing should be null. And the solution is that it has the form 1 little x squared little x mu, where little x mu is in RD. And so this gives a copy of RD inside the embedding space. And I guess I'll call this thing capital X of little x. And the metric on RD you can get by taking D by it's just obtained by pulling back the metric on the embedding space. So we compute d capital X of little x dot d capital X of little x, and you can check for yourself as an exercise that this is equal to the usual metric on Euclidean space. And the whole point of this is that we get in a very natural way the action of the conformal group on Euclidean space. And the idea is to start on the Poincare section and act by an element of the conformal group, so G in SOD plus 1, 1, where G is just a D plus 2 by D plus 2 matrix. Okay, so it acts as a matrix on this vector. After acting with G, we generically are not on the Poincare section anymore. Okay, so we started on the Poincare section, but we acted with G. It sent us somewhere else off the Poincare section. So we have to rescale. We use the rescaling gauge redundancy here to go back to the Poincare section. And that means we have to divide by the plus component of this thing. And this is now back on the Poincare section, so we can write it as x of little x prime. And so overall, we get a map from little x to little x prime, which is generically a nonlinear map because it has something in the denominator. And this is the nonlinear action of the conformal group on RD. So the Poincare section is one thing that we can, one slice of the projective null cone that we can take, but we could imagine other slices, and other slices of the projective null cone give other conformal metrics on RD, by which I really mean SD. And so, for example, suppose we pick a different gauge fixing of rescaling. We set x plus equal to omega of little x. Then the way we get the new metric on little x is we take d of the new embedding space vector. The new embedding space vector will be omega of little x times capital X of little x. Right? So this thing satisfies this gauge condition. And we want to dot this with itself. And this is just equal to omega of x squared times dx squared. Why? Well, first of all, if the d doesn't hit omega, then this is the answer we get. Suppose the d hits one of the capital X's. Well, d capital X dot x is 0, and x dot x is also 0. Okay, so we have this null cone condition that x dot x is 0, and taking derivative of it, we get this condition. Right. So as a consequence, the terms where the d hits omega drop out, and we just end up with this. Okay. All right. So the idea then is that by taking different slices of the null cone, we get different conformal metrics on this space, and we're going to use that in a second. And the last comment I want to make about the Euclidean embedding space is that it's easy to go back and forth between different conformal frames. So if you have a Euclidean correlation function in one conformal frame, let's say with metric G, then this is related by just some rescaling factors to the correlation function in a different conformal frame. Where the metric has been rescaled by omega squared.
Do you put some positivity on lambda? Because if you just allow lambda to be negative, then it should be like a real projective space rather than a sphere.
It's not real projective space because the question was, if you allow lambda to be negative, then shouldn't you get real projective space and not a sphere? And the answer is that we're projectivizing this quadric. We're not projectivizing all of space. If we projectivized all of space, we'd get real projective space. And here you can see explicitly that letting lambda be positive or negative just means that we can ignore the bottom cone. Right? We can always use the sign of lambda to put us in the top cone, and then we can rescale by positive rescalings in the top cone. Any other questions? Okay, good. So that's the Euclidean embedding space. And so far, it's given us just a fancy way of looking at Euclidean correlators. And so now, let's analytically continue to Lorentzian signature. So from now on, I'm going to use E subscripts because we're now going to have the Euclidean embedding space and the Lorentzian embedding space. So I'm going to start introducing subscripts to disambiguate them. Okay. So everything that I was talking about here so far was Euclidean, but now we're going to have both. So let's start with a Euclidean point. And we're going to do our usual analytic continuation, where we write x Euclidean 0 is equal to I x Lorentzian 0. Okay. And so what we should do is, so let's say we start in the Poincare section. So we start with this vector, and we replace and we make this replacement. Then we're going to end up in a Lorentzian embedding space on an analog of the Poincare section in the Lorentzian embedding space. So we're going to define, so Lorentzian embedding space is RD comma 2. And we'll define coordinates. So I'll denote a vector in this space by XL. And the coordinates of XE and XL will just be related by a factor of I in the 0th component. Okay? So we have this relation, and all the other coordinates will just be the same. So this is just, it's just a different labeling of the same complex space, if you like, where it's a different labeling of the coordinates on C D plus 2. Okay? So if we make this definition, then the metric on the Lorentzian embedding space is XL squared is minus XL plus XL minus. It's just the same as in the Euclidean case. The only difference is because of this factor of I, we get a minus sign for the time coordinate. Okay? And so, okay, so now the point of all of this is that after this continuation, we end up with a Lorentzian version of the Poincare section where XL is equal to 1 comma XL squared comma XL, where of course XL is equal to XL0 X. Okay, so the only thing I did is I introduced a factor of I here, and then I removed it with this definition. Okay? Questions? Good. Okay. So the idea is you start on the Poincare section in Euclidean embedding space, you analytically continue the time coordinate, and you land on the Poincare section in the Lorentzian embedding space. Now, the whole point of all of this was the claim that we can go beyond the Poincare section in the Lorentzian embedding space by doing something a little bit more clever, choosing a different time coordinate with which to analytically continue. The Hamiltonian that I said we were going to use was this funny combination of different conformal generators, P0 minus K0. And so P0 minus K0 is the generator of the conformal group corresponding to a conformal killing vector that I'll call tornado. Tornado is 1/2 P0 minus K0, where now these guys are lowercase. I think Slava introduced this, these different conformal killing vectors. Did he? Good. He even talked about the Lusher-Mack Hamiltonian, I think, right? I'm using a different sign convention for K from him, but anyway, you can look at his notes. So this thing, oh, let's see, I think I wrote it somewhere. So it's some funny conformal killing vector. It's 1/2 1 plus x squared d0 minus x0 x dot del. Okay. Now, to understand what happens when we use this thing as a Hamiltonian, it is very helpful to change conformal frame and turn our conformal killing vector into a regular old killing vector, namely an isometry. Okay? So that is the whole point of this embedding formalism that I introduced now. It makes it totally trivial to change conformal frame. The way to change conformal frames is to just choose different slices here of the projective null cone. So I'm now going to choose a different slice that turns this crazy conformal killing vector into a regular old isometry. Okay? And so, okay, so what's the slice? The idea is to choose so we're going to choose a different slice of the projective null cone. which is equivalent to some choice of conformal frame. And the slice that we'll choose is parameterized by, so we're talking for now about the Euclidean embedding space. It's parameterized by eta, which is a real number, and n, which is a unit vector in d dimensions, or equivalently a point on the d-1 sphere. And so let me write out the coordinates of xe, just to remind you. So x plus, x minus, and I'll single out the x0 coordinate, because of course that's going to be one of the most interesting ones. And then the spatial coordinates, where I runs from 1 to d-1. And we're going to set this equal to cosh eta plus nd, cosh eta minus nd, sinh eta, and I. Okay, so exercise. Check that this vector is null. Okay. And another exercise. Compute the induced metric and show that it's equal to d eta squared plus d omega d-1 squared. In particular, that's the metric on a Euclidean cylinder. So I think a picture is worth 1,000 calculations in this case. So let me try to draw what we just did. So the Euclidean cylinder should look familiar to you guys. That's what you get when you do radial quantization. And what we've just done is changed conformal frame to one appropriate for radial quantization between 2 points. Okay? And the 2 points that we're doing radial quantization between, by doing radial quantization between 2 points, I mean that one of the points is the point at past infinity on the cylinder, and the other one is at future infinity on the cylinder. Those 2 points are precisely the fixed points of this conformal killing vector. Okay? And Slava may have drawn these pictures, I'm not sure. So the idea is that this conformal killing vector has 2 fixed points. At x0 equals plus or minus 1. And the flows have this funny shape. But I don't mean flows. These are the images of this spatial surface under flowing with respect to this conformal killing vector. Okay, so it has these 2 fixed points, and what we've just done is made a conformal transformation to the cylinder, or sorry, a change of conformal frame to the cylinder, so that this original spatial slice here becomes an SD-1. And now the flows are just like this. Okay, it just gets translated in time, where time is now eta. Any questions? Okay, good. So we've turned this conformal killing vector into an isometry. And now that it's an isometry, it's really easy to see what happens when we analytically continue. In particular, so let's set eta equal to I times sigma, and the metric we're going to get is minus d sigma squared plus d omega d minus 1 squared. And this is the metric on r cross sd minus 1, where now the r direction is Lorentzian time. So this is called the Lorentzian cylinder. And I'll sometimes denote it with this funny notation, which means the universal cover of the conformal compactification of Minkowski space. Okay.
I was about to say, another way this could have been introduced into the standard conformal compactification to the diamond of Minkowski space, and then you say just continue drawing it.
Absolutely, that's exactly right. And hopefully the picture that I draw in a second will make clear that that's what you're doing. So the idea is, so when we do this analytic continuation, we end up with this now Lorentzian cylinder. And you can ask where Minkowski space is in this picture. Okay, so before drawing that, let me just explain how you calculate the answer. Okay, so the idea is that we have this embedding space vector, this Euclidean embedding space vector, and we can now continue it. We plug in eta equals I times sigma, and we end up with a Lorentzian embedding space vector, which is a function of sigma and n, where the coshs and sinches have been replaced with cosines and sines. Now, when we plug in eta equals I times sigma, we actually get I sine sigma, but that's I sine sigma, that's equal to x Euclidean 0, and x Euclidean 0 is equal to I x Lorentzian 0, so x Lorentzian 0 is just sine sigma. Okay, so that's where that comes from. And then finally ni. So this thing parameterizes an S1 cross SD minus 1 inside the Lorentzian projective null cone, which is not quite the right answer. So the problem is, well, I already told you what the correct answer is. The problem is that even though the embedding space coordinate is periodic under sigma goes to sigma plus 2 pi, the physics is not. Okay, so the physics is not periodic under sigma goes to sigma plus 2 pi. And why is that? Well, one of the nice things about this construction is you can see we know exactly what the spectrum of this Hamiltonian is. The Hamiltonian that we're using is equivalent to the time translation operator on the Euclidean cylinder, which is exactly the dilatation operator of the CFT. Okay, so the spectrum of this Hamiltonian is the dilatation operator, and in particular, when we time evolve with this Hamiltonian, we end up with phases that look like e to the minus I sigma delta, where delta are conformal dimensions, and generically the conformal dimensions are not integers, and therefore these phases are not periodic under sigma goes to sigma plus 2 pi. Okay, so even though the embedding space coordinate is periodic, it's not a complete coordinate on the space that we actually land on. The correct space is the universal cover of this, which is, of course, the Lorentzian cylinder. Okay, but okay. So what was the point? The point here was that this gives us a way of understanding where in the Lorentzian cylinder the Poincare patch lands. Okay, so here's a Lorentzian embedding space vector, and it doesn't cover the entire Lorentzian cylinder, but it covers a patch of it, 2 pi patch. So the actual point on the cylinder is specified by saying, by giving the embedding space vector and also saying how many times you have to translate by 2 pi. Okay, and so now what we can do is equate this embedding space vector to this embedding space vector and figure out the relationship between sigma and n and xl. Okay, and so to do that, we have to take this thing and rescale it so that it's on the Poincare section. And so we get, that means we have to divide by this. So we get this relationship cosine sigma minus nd over cosine sigma plus nd sine sigma over cos sigma plus nd ni over cos sigma plus nd. Okay, so using this relationship, you can check for yourself that as XL ranges over Minkowski space, you only cover part of the space described by the sigma and n coordinates. And I'll just write the answer, and I'll leave it as an exercise to compute it from this expression. The statement is that XL covers a Minkowski patch, which I'll try to draw, which looks like a diamond. And the reason it's a little bit difficult to draw is that the diamond wraps around the cylinder. Okay, so the idea is that we have this diamond and it's wrapping around, and the tips of the diamond are touching the point here, which is the point at spatial infinity in Minkowski space. And so now we can understand what's going on with this funny Lucier and Mach Hamiltonian. And to see that, let me unwrap the cylinder.
For about 2 minutes or
Oh, okay, great. Okay, so I'll unwrap the cylinder. So now these two sides, these two lines should be identified. And we have our copy of Minkowski space sitting in the middle. And the idea is that the usual Minkowski time describes, if you evolve by the usual Minkowski time, you get slices that look like this. Okay, so these are the things that you get by exponentiating P0. And all we did is we chose to exponentiate something else, which is the global time generator on the Lorentzian cylinder. So instead of exponentiating that, we decided to exponentiate something that does this. So that's the thing generated by the Lucier-Mach Hamiltonian. And that, of course, lets us go outside of Minkowski space and explore this whole new world out there. And we get this for free in conformal field theory because we can easily change conformal frame and write the correlators as functions of n and eta. And then the Hamiltonian that describes the flow in eta is just the dilatation operator, which in particular is positive. It's positive and it has a real spectrum. And because it's positive, bounded from below, unbounded above, all of our technology from before applies. And so we can continue to get Whiteman functions on the Lorentzian cylinder in the same way that we talked about before. Okay? So we've arrived at this statement due to Lucier and Mach, which I'll just write and then I'll stop. So the statement is that correlators in a unitary or equivalently reflection positive CFT can be continued to Whiteman distributions. Okay, so all the subtleties we've talked about before are still true on the Lorentzian cylinder. Okay, so next time we'll talk about some observables that you can define in Lorentzian signature that are very difficult to make sense of in Euclidean signature, and to fully understand these observables and their properties, it will be extremely useful to think about them living on the Lorentzian cylinder and not just in Minkowski space. Okay, so I'll stop there. Thanks. Yeah.
If you were to do something similar, but instead with the usual time Minkowski with the boost operator, with the boost translation, sorry, like so that you get like the return match, what would you get?
So if you used a boost, let's see. I would have to think about it. So let's see. So a boost generator is a different kind of generator. I think that the so first of all, the right-hand side would get boosted. Maybe I need to. Well, I'll try. I'll draw a different picture. Right over here. So here's Minkowski space. Here's a spatial slice. And now let's start boosting it. Okay, so the right-hand side gets boosted. So that means that we know at least we understand this part, right? The point at spatial infinity is actually fixed. So what we need to do is that. And of course, the other side gets boosted the other way. So we have something like this. So the images of these slices look something like that. And as we boost things a lot, they get boosted towards these points at future null infinity and past null infinity. And I could draw what happens if we do negative boosts. Okay, and so as you boost, you never pass. Well, I committed this in here. You never pass these horizons, and let's see. And then you can ask what happens here in this region. So in this region, if you start with this line and you boost it, then you get lines that look like that. And so here you can see something kind of interesting, which is that the boost generator around the origin actually behaves like a dilatation operator around a point at null infinity. So everything is being pushed towards this point at null infinity, and if you completed the picture, you would find that things are being pushed in that way. Does that answer the question? Okay. Yeah, we'll actually use this fact next time.
Don't forget the dinner at 6 in Koenig. Bring your name tag. I did a quick offline question.
Yeah.
So the important part about the